Okay. Good morning, my dear students. Today we are going to discuss about the matrices, right? Matrices is a very simple topic for you. It's a new topic, but it is very interesting for you, right? Before going to this part, we quickly recall about something in our knowledge that what is a array are rows or columns, right? A function, right? A function or group of elements arranged in rows and columns. Means you can call as arrays. Is a matrix. So fundamentally, matrix is a function, right? Or it can be a set or group of elements, right? Arranged in rows and columns. What is a row? Something A11, A12, A13, A14, etc. A1n, first to nth column. This is A21, A22, A23, A24, etc. A2n. A31, A32, A33, A34, etc. A3n. Then you proceed like this. AN1, AN2, AN3, AN4. Sorry, here M I can take. M1, M2, M3, M4. Here AMN. Right? So there are these horizontal things are called horizontal lines. Lines are rows, right? And vertical line are columns. So these are vertical, right? These are vertical lines, they are columns, and these are horizontal lines. They are rows, right? Now this all of them are represented or bounded in a set or in a box or something you call as a function because it's containing some elements, right? Function is also relation is also some element only. Likewise, okay, you can take likewise. This is represented with a capital A, suppose. So this is a matrix A with here how many rows are there? M rows. So I can write this part here visible bit upper. AM1, AM2, AM3, AM4, etc. AM. Right? So in that case, what happens? You can take M rows and here how many rows are there? There are 1, 2, 3, etc. Column rows are M and columns are 1, 2, 3, etc. N columns. So there are M rows and N columns. Are you clear? So M rows and N columns with this is a matrix. What is a matrix? Again, I am recalling clearly. A matrix is a set of or group of elements arranged in either in rows and columns, or they are called arrays. Arrays means rows and columns. General name is array, and it's fundamentally a function because it contains some elements with some order or some what you can say with some meaningful or purposeful what you can say arrangement. So this is called an element or all these are called as elements, right? This is one element, elements of a matrix, 1, 2, 3, 4, right? These are also elements. So how many elements are there? Totally m rows into n columns, m elements. So what is the order? Right? I think you are clear with this part, right? Okay, once again I'm saying a matrix is a set of elements which are arranged either in rows as well as columns. There are some matrices we can discuss them which have only rows or which have only columns like that. That's different case, right? One row, one column like that. But standardly we are taking some matrix as with n rows and n columns. This is the location of the element. This is the first row, first column, right? So this is first row, second column, first row, third column, like that, right? So generally is that element is always totally m elements is there because m rows and n columns totally it's like a square or rectangle like that. Multiplied the number of like length into breadth, right? Clearly. So m rows into n columns is called totally mn elements of the given matrix. Like what is the order? Order of the matrix is order of the matrix m by n. We write into, but it is called as by. Order of the matrix is m by n. So what do we have here? We write first here rows, and here you write here columns. So first you write the order as rows into or by columns. Suppose I wrote, I think you are clear with this part, right? I took a general formula or a general representation for the matrix. I look for a specific one, right? This part of notes also I will send you. There is nothing to worry because this is very simple concept. We can easily do this part and understand it also. If you go to the textbook or any reference source for this, you can easily understand. Still, I will be able to guide you where you have to do. This topic has matrices has 1 marks, 2 marks, and 4 marks types, or sometimes it can be 6 marks also. Right? Here, number of elements are as order on that space. 1 mark can be, right? And 2 marks can be finding inverse, right? For 2 by 2, and but you can say symmetric, skew symmetric. I am discussing the models, right? And 4 or 6 marks can be finding inverse of the matrix. Similarly, this is symmetrical, skew symmetrical be, and here construction of matrix also will come for construction of matrix. Right, and here this may come for 1 mark, this may come for 2, and inverse can be coming for 4, symmetric, skew symmetry also can be 4, depending upon the number of steps and the length of the question or complexity of the question. And finally, inverse of the matrix is by elementary operations. This is very important. Already I have discussed this answer for you when some of you asked that doubt how to proceed. Row or column, elementary operations, right? This question we will discuss clearly. So we'll go detail about all these models, no need to worry. So it can have 1 marks generally, 2 marks generally, and 4 marks also. And sometimes it may come to, depending on the length of the question, it can come to 6 also. 4 can be 4 and 6, 2 can be 2 and 4, 1 can be 1 and 2, like that. These are expected models for this topic. We go in detail, everything when we go one to one, right? Now coming to this part, already we understood what is a matrix, right? We'll see the types of matrices and their properties, right? We'll discuss that later. First we go with a general case. Matrix can be order is m by n rows and n columns, right? If I take a matrix, are represented always with capital letters. Matrices are with capital letters. Matrices are always denoted with the capital letters. So I can take capital A, capital B, capital C, capital D, capital X, capital Y, capital O, capital P, capital Q, like that. Mostly capital letters. And the elements are small letters. Always small letters. This is standard way of indicating the matrices, right? Now, if I take here a matrix like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It is a matrix, right? How many rows are there? 1, 2, 3. How many columns are there? 1, 2, 3, 4. So the matrix is of order 3 by 2. So there are 3 rows and 4 columns. You can easily see this vertical is column 1, 2, 3, and 4 columns. And horizontal is rows. You know horizontally, rows will be horizontally and columns will be vertically always. Right? I think you are clear with this part. So this is of the order 3 by 4. Right? So let me take one example again. A, B, C, D, E, F, G, H, I. Then you may get an idea. This is matrix B. As the elements can be anything, not only numbers, it can be letters also, it can be alphabets also, or it can be some symbols also. But mostly we are with either numbers or letters, right? Symbols are rare cases, we are not discussing that part. So A, B is equal to A, B, C, D, E, F, G, H, I. Here how many rows and how many columns are there? 3 rows and 3 columns. This is called a square matrix. Why? Here M is equal to N. Number of rows are equal to number of columns. That's why this is called a square matrix. Right? Now, in this case, number of rows is not equal to number of columns. M is not equal to N. So this is called a rectangular matrix. Because naturally we know what is rectangle, length is not equal to breadth. Either one of them can be bigger than or them different to others, and one can be smaller, one can be bigger. So it is rectangle. But in the case of a square, the sides are equal and the length is equal to breadth. Technically, we say it is called a square. So this is square matrix. Number of rows are equal to number of columns, and this is rectangular matrix, right? So matrix can be any one type, either square or rectangular, but not none of them. So any matrix can be of the form either square matrix or rectangular matrix, but not both. Are you clear? So all the nature of the matrix will be decided by the order. Order is number of rows into number of columns by. But when we are reading it, we call it as M by N. Right? By we indicate it as a into only, we can say. Right? I think you are clear with this part. So the nature of the matrix are decided by the order and its number of rows as well as number of columns. Order is nothing but number of rows and number of columns. Now, here we can take here first 1 minus 1, 2, 2 minus 3, 1, 3 minus 2, 4. Right? So what are the elements? They can be negative numbers, positive numbers, integers, rational numbers, irrational numbers, and even they can be complex numbers also. The elements can be any real number or you can take any number system. So generally, elements are 1, 2, 3. This is first row, first column. So I got as corresponding to this, I can write this as A1, 1. First row, first column. This is first row, second column. So I call this as 1, 2. This as 1, 3. Because here is the small a is the identity or the standard way of representing the matrix, elements of that. This is A2, 1. Second row, first column. This is A2, 2. This is A2, 3. Second row, third column. And this is A3, 1. This is A3, 2. This is A3, 3. So this is A11, A22, A33. Here, what is what? Here I call this as general name is IJ because already I have used M and N. So AIJ. So ith position, right? AIJ 1, 1. Here I is equal to 1, J is equal to 1. Row, the position in the row is first and the position in the row is second. Here A22, position in the row is second and the position in the column also second. A33, position in the row is third row and third column. Second row, second column, first row, first column, third row, third column. Now here M is equal to N. So here it becomes AII or AJJ. We can take this. If the elements are lying in the order of principal diagonal of a matrix. So this one where in this way slant from left to right, left up to down right. Not this. This also diagonally. But what is this? A31, A22, A13. They are not same. Here 1, 1, 2, 2, 3, 3. So this is only diagonal. Remember it. Diagonal can be in this also you can go. But this is because what we are specifying with respect to diagonal of the elements, the location of the element with respect to row and column must be same. It should be first row, first column, or second row, second column, third row, third column. All of them are in the same order to form a diagonal of the given matrix. You know what is a diagonal, right? For a figure, closed figure like a rectangle or a parallelogram, you know what is a diagonal. So same way, this is called the diagonal or principal diagonal of the matrix. These are also diagonals, but they are not a principal diagonals, right? So slant are diagonals, but this is a principal diagonal, right? So these elements are called diagonals. Now you understand the location of the elements, right? So what is the general location of an element in a matrix? General location of an element in a matrix is Aij, where ith row and jth column. This is indicated with the ith row and jth column, right? Ith row and jth column means Aij is the location of the element in the given matrix, right? You can note it down if you want. Right. Based on your square matrix, you know, rectangular matrix, you know, and now you have understood that if in these cases, remaining all, suppose I took as zeros, something you figure is B. So Aij is equal to A, I is equal to J is how we can represent this as this element, what you can say matrix Aij, where I is equal to J is not equal to 0 and Aij is equal to 0 where I is not equal to J. Here I is equal to J cases, they are non-zeros, and I is equal to not equal to J cases, they are zeros. So this is called as diagonal matrix, because only diagonalize. You understand now? The condition of saying it is Aij is not equal to 0 where I is equal to J, Aij is equal to 0 where I is not equal to 0, J. See here 0, here is equal to, here not equal to, here not equal to, here equal to. Such matrices are called diagonal matrix. Now we see the example here, diagonal matrix, right? Okay, understand now what is diagonal? Location of the understand now. We are discussing about a type of matrices here, right? Next, I take this case. One. So the principal diagonal elements are always completely equal to 1. So the principal diagonal contains only one element, 1 each case. So Aij is equal to, where I is equal to J is equal to 1. It's fixed. Aij is equal to 0 where I is not equal to J. Then this is called the unit matrix or identity matrix. Aij is equal to 1 where I is equal to J. Aij is equal to 0 where I is not equal to J. It is called identity matrix. Rest. Now it is a square matrix 3 by 3. This is identity matrix of 3 by 3. So I denote it as I3. Suppose there is 1 0 0 1. This is called I2. Because identity matrix is denoted by I and follow with order. Denoted. This is the short way of doing it. I2 is 2 by 2 matrix, square matrix of order, identity matrix of 2 by 2 square matrix. 1 0 0 1. Principal diagonal is 1 1, right? So in the identity matrix, principal diagonal consists of only element 1. Are you clear? In the identity matrix, principal diagonal will be having the value as 1 and other elements are zeros. So ideal matrix of can be ordered. I1 cannot be there because I1 is automatically it will be 1 by 1. 1 by 1 should not have anything. So I want to go for I4. Yes, it can be there 4 by 4. And identity matrix is only for square matrix because diagonal exists for square only. Rectangle you can't have diagonal. Suppose I took the diagonal like this 4, 5, 6. Here what is diagonal? This is 3 rows and sorry 2 rows and 3 columns. There is no diagonal here, right? Diagonal is will be holding only for square matrices. So identity matrices are always square matrices because we are talking about the diagonal elements are 1 and other elements are 0. So identity matrix will be having only a square matrix. Right now I can take as 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0. This is 4 by 4 or denoted as I4. Right? Okay, in this case we can go as 4 by 4, 4 rows and 4 columns. Naturally, we can get as 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. So identity matrices are always square matrices, right? Now we have seen diagonal matrix. Next, similarly we have seen identity matrix, right? The conditions also we are discussing clearly. Now, suppose here all the principal diagonal elements are 5. So clearly I can write this as multiples of all the elements where it is showing us Aij is equal to some k, right? Where I is equal to j and A is equal to 0. Some constant will be there fixed instead of 1. Then this is called a scalar matrix. Scalar means you are multiplying the number, right? Can I take 5 common likewise? Then it becomes 5 into 1 0 0 0 1 0 0 0 1. This will discuss that how to multiply all these things, right? We can go with 5 common and it will be 1 0 0 0 1 0 and 0 0 1. So this is called a scalar matrix such that Aij is equal to instead of 1 k for I is equal to j and Aij is equal to 0 where I is not equal to j. This is called a scalar matrix, right? Now we have seen identity matrix, diagonal matrix, square matrix, order of the matrix, location of the element Aij, ith row and jth column, and order of the matrices, right? So after knowing these things, now we'll go for operations and these things. Next, how to do the operations? We'll discuss that part now, right? Among the matrices, I'll give an example how to proceed. Next, still there is other types, a row matrix. A row matrix. If there is only one row, and any number of columns in a matrix, then it is row matrix. So I take suppose A is equal to one row. 1, 2, 3, 4, 5, 6, 7, 8. Here all rows are there, only one row, and columns are there 1, 2, 3, 4, 5, 6. This is 1 by 8. So this is a row matrix, right? One row and n columns. Generally it is indicated as 1 by n because m is always 1. N is the number of columns. N can be any number, right? Now what about column matrix? If there is only one column, and any number of rows in a matrix, then it is column matrix. So what is the order of the column matrix? We'll see now. Suppose you take as something B is equal to 1, 2, 3, 4, 5, 6. Here how many rows are there? 6 rows and column is 1. Only one column. So this is indicated by what is the order? M by 1. Here 1 by n and here m by 1. M rows and 1 column. Rows are horizontally 1, 2, 3, 4, 5, 6. So 6 rows and 1 column. So it is m by 1. And here 1, 2, 3, 4, 5, 6, 7, 8. This is 1 by 8. 1 row and n columns, right? So order depending upon the number of elements, rows or columns, right? This is there. Now, if there are m rows and n columns, this is simple common sense question. The matrix has m rows and n columns, then the number of elements, automatically you know it, are m into n. Here 61 6 elements are there, here 1 into 8 elements are there. There are m rows and n columns, suppose 1, 2, 3, 4, 5, 6. Here how many rows are there? 2. And columns are there how many? 3. So how many total elements are there? 6 elements. 2 into 3, 6. Instead of taking any number, the number of elements are same only. Right? So you can take the number of elements of the given matrix is the product of the number of rows and number of columns. Right? M rows and n columns. I think you are able to understand very simple in this case, because there is no complexity in understanding this part, because the concept is a very simple common sense part, so easily we can do this part, right? Next, negative of a matrix. Negative of a matrix. Suppose I took A is equal to some A, B, C, X, Y, Z, P, Q, R, or minus X, minus C, minus Q, like this. Suppose, right? What is minus A? Indirectly, minus A is minus 1 into J, right? This is minus A is the additive inverse or negative of matrix A is a negative of matrix A or additive inverse of matrix A, such that how it becomes then minus 1 you multiply with every element. So minus A is equal to minus 1 into A, which is nothing but multiply with minus 1. So minus 1 into A, minus A, B into minus 1, minus B, minus C into minus 1, C. So elements will keep changing their signs. Minus P, Q, minus R. Now you understood that. So every element, so for every Aij belongs to capital A, minus Aij belongs to minus A. So for every element, automatically symbol changes, minus Aij. So this is the general location of the element is Aij. So A11, A12, A13, A21, A22, A23, A31, A32, A33. So all such cases, if we add, what happens? Aij belongs to A, minus of Aij belongs to minus A. Already it is minus, it becomes plus. If it is plus means it becomes minus. This is called the negative of matrix. The negative of matrix is nothing but negative inverse. Why negative inverse? See here. Add A with minus A. Minus A. Right? So automatically you can take it as here A plus minus A. Here minus A, B, C, minus B, X, minus Y, minus Z, minus P, Q, minus R. Right? Now, how to add the matrices? It comes to that. Whenever we are taking the operation addition of matrices. If two matrices can be added, what is the condition first we should know? Every two matrices cannot be added, right? So corresponding elements, suppose I take here Aij plus, similarly we can take Bij, have added. Then automatically you get Cij for all I comma j belongs to A. So I comma j belongs to A means it should have same order, because suppose here 1, 2, 3, 4 plus 2, 3, 5, 1, 4, 7. Can I add? How I can add them? Here this order is 2 by 2, here 2 by 3. See, 1 I can add to 2, then how I can add 2 to 2, which I have added? So I cannot have corresponding elements to be added. That means to have the addition of matrices possible, always we should see that the orders must be the same. Then corresponding elements, like corresponding elements, we have to go. You know corresponding elements, right? Corresponding elements can be added, and they form again an element. Similarly, so I can take now here just add those two. So automatically A plus minus A, B plus minus B, minus C plus C, minus X plus X, Y plus minus Y, Z plus minus Z, similarly P plus minus P, minus Q plus Q, minus R plus minus R. This is what you can have. Right? Now everywhere you take the respective elements. First element, first column is added to first and first column, second element, second matrix. First element, second column is added to corresponding first and second element of the second matrix. First element, third column of the first matrix is added to corresponding first row and third column of the second matrix. Like that we are added, and resulting one is coming always completely. So all the zeros are coming. That's why this is called, for this matrix, this is the I2 inverse. So what is I2 inverse? A plus minus A automatically becomes 0, or if I add minus A plus A also, because the elements are commutative. Instead of A plus minus A, I can add minus A plus A also, automatically 0. This is indicated as 0 or both. Right? So this is called a zero matrix. All the elements of a matrix are zeros, then it's called the zero matrix. And what is the condition for addition of matrices? The orders must be same. The two matrices must be of same order. Otherwise, they cannot be added. Once we say orders are equal, the automatic number of rows and number of columns are equal. Then only you can get the corresponding elements feasible to be added now. Likewise. Okay? So, like you can see, number of elements correspondingly are able to be added, and they form to become their sum form to be 0. So if all the elements of a matrix are zeros, then this is called zero matrix, or the other name is null matrix. Null. So what is the identity? How I can say? Indication must be there for every matrix you have to say, right? So the indication must be for every Aij and Bij added to become Cij. If Cij becomes 0 by adding the two matrices, then the matrix becomes zero matrix or null matrix. And each matrix is the reciprocal or inverse to other. It is called the inverse. So this is the inverse of A is the inverse of minus A. Indirectly additive inverse. Inverse means there are two cases. Again, multiplicative inverse also there we have seen in the first chapter. Inverses can be either additive or multiplicative also. So this is minus A is the additive inverse of A, and A is the additive inverse of minus A. Such that A plus minus A or minus A plus A is equal to 0, and 0 is called the big zero we write, because all the elements are small zeros and we can write big zero. It's always, so this indicator as like this. So null matrix are, it's called a zero matrix. So how I can indicate in a general form for a zero matrix? So we have seen negative of a matrix is nothing but negative inverse, and the negative inverse is formed automatically for a given matrix. Their sum should be always coming to zero matrix. So you can tell here if A is equal to 0, then for all Aij is equal to 0. Every element, its location is 0. Aij, A11, A12, A13 is 0. Everything. A21 0, A22 0, A23 0, A31 0, A32 0, A33 0. Likewise, you can go for all Aij is equal to 0. So 0 is called the 0 matrix, right? Next, negative over 0 matrix over, and we have seen row matrix, column matrix, and similarly, what is left over, we'll see just cases. Right. Equality of masses. We'll see this part. Right? A for every suppose I can A 1 2 3 0. B is 1 2 3 minus 1. Now for each element A I J is not equal to B I J, right? Where A I J belongs to A and B I J belongs to B. Every element is not equal to each other. Because here one corresponding A11 is matching with A11 equal, A21 is matching with A22 equal, A31 is A21 is matching with A21, but A22 is not matching with. Here since A22 is not equal to B22. Here A22 belongs to capital A and B22 belongs to capital B. Here B1, B21, B11, B12 I can get like that. Because so that each element is not matching. Suppose I take here also 0, then automatically for every Aij is equal to Bij, right? The matrices A and B are said to be equal. Now here we are equal matrix. Otherwise you cannot compare the corresponding elements, and the corresponding elements also should be equal. So there should be orders equal and elements also correspondingly equal. Then only they are called as equal matrices. Or it is nothing but the condition prevailing, or the condition satisfying is called the equality of the matrices, right? Now we have seen order, elements, rows, columns, location, right? Inverse, anti-inverse or negation of the matrix, scalar matrix, diagonal, principal diagonal matrix or unit matrix, order of the unit matrix I1, I2, I3, likewise I4 also we can see. Next, what else left? Product of the matrix, scalar matrix means 5 into I, like that, anything you can take. Now we have seen the how the matrices are to be compared. Addition is more. Same way, subtraction also we can do the same. Subtraction of two matrices. It is nothing but addition only, na? A minus B 1. So A plus minus B. So find the inverse of B and then add 2. So it is the same only. The two matrices should be same order because then only you can subtract of same order. Otherwise, they are not able to be subtracted. Right? Subtraction two matrices is A minus B is A plus minus B. The two matrices should be of same order. And addition also should be same order. Otherwise, it cannot possible to have the addition also, right? A plus B is possible only when A and B are of the same order. Similar subtraction also. Division and multiplication we discussed later because division is not taken in other way, finding with multiply with inverse, such that A by B is equal to A into 1 by B or A into B inverse. And what you can say, multiplication is has different order, right? That condition is there, A into B. So this is about the subtraction of matrices. So to have the addition and subtraction, fundamental operators, right? You should have always their orders must be equal, right? Next. Lastly, we discussed about the division and then finding the inverse. Now we discuss about the product of the two matrices. That is called multiplication of matrices. So I put here A 1, 2, 3, 4, 5, 6. What is the order? 2 rows and 3 columns. Right? So I can take this as M by P. Right? Then I want to find AB. That is nothing but a product of A and B. Right? I should take B order such that it should be anything but P by N. So here number of columns must be equal to here number of rows. Right, means these two should be there as equal. So in order to have, why? I'll tell you. The multiplication feasible. Again, it varies with BA. With the order we change now, I'm talking about it. The first matrix number of columns are equal to the second matrix number of rows. Because the process I will tell you how to go. In order to have multiplication feasible, the number of columns of the first matrix, because we are talking about AB here. So A is the first matrix, B is the second matrix. The latter, right? The number, in order to have multiplication feasible, the number of columns of the first matrix should be equal to number of rows of the second matrix. So here M by P means here P is 3. So 3 by anything you can take. 3 by 4 or 3 by 2, 3 by 1. Anything you can take. N can be anything. Suppose 3 by, I can take as 4, suppose. So 3 rows and 4 columns I should take. Right? I can take. Only this is possible. Why I tell you? Because the process requires this equality. Only this case. So in order to have the feasibility of matrix multiplication, right? You should have the number of columns of the first matrix should be equal to number of rows of the second matrix in the order of the multiplication. In the order of multiplication. So if A is the first element, the first matrix of the order AB, we are fine. Suppose for BA, again we should have the review because BA means 3 by 4. Here 4 should be equal to, we have to go with 4 here, right? Likewise. Suppose this is 2 by 3 by 4. So I can take here 1 minus 1, 2, 3. 3 rows and 4 columns. 2 minus 5 1 3, 4 minus 3 2 1. What is this? 3 rows and 4 columns here. Right? Now, actually how to go about, we'll see it. I'll see in general. Do you understand the condition? And the result after multiplication. So if A into B, again you are getting C. You get again a matrix, the order of C must be, you want the common part and take the other part. It should be having the number. So order of C is the number of rows of first column and number of columns of the second column. Leave out the common part, easy part, equal part, which you are comparing, that part will be written out and you'll get M by N. So the output of the matrix you are getting here, C is, here for this case, 2 by 3, 3 by 4. So what comes here? 2 by 4. Because 3 is common in take out. I'll show this example how you will take the part of the matrix. Because it is only the bit complicated process in the entire matrices, product of the matrices. You should be very much careful and vigilant when you are understanding and doing it. See, matrices involves most of them arithmetical operations, right? Elementary operations, they are also will be followed later. So they involve fundamental arithmetical operations. So your attention and concentration in doing the simple multiplications, addition, subtraction is very much required. If you do 2 into 3 plus 4 is equal to, not equal to 10, or you wrote 2 into 7 as 14, then you are wrong. So fundamental basic operations of addition, subtraction of numbers, you should be able to follow. So process of multiplication we are not yet completed. We have seen the basic condition. So what is the condition for a multiplication to be possible between two matrices? The number of rows of the first matrix will be equal to number of columns of the second matrix. Why this? Sir, why not others? Like why they cannot be orders are equal like that? Here orders are not equal. But you can have anything to be taken. But it should have the equality such that the number of rows of the first matrix is equal to number of columns of the second matrix. And the order of the output matrix is equal to number of rows of the first matrix into number of columns of the second matrix. Right? Are you clear? So in this case, I'll give you an example. So this is 3 by 4 as I took. Here A is equal to 1, 2, 3, 4, 5, 6. 2 rows, 3 columns, right? Now 3 is equal to 3 is match. Now out of the output matrix is equal to C. Now I'm going for A into B, right? Part of the matrix. So I start with this left hand is first matrix is A, second matrix is B. So I take here this row and corresponding I'll go with this column, right? Okay. So I'll take corresponding multiplication also. 1 into 1 plus 2 into 2. So I'll write down easier. Plus 3 into 4. Right? Over. Again, first row, second column, I'll come here. 1 into minus 1 plus 2 into minus 5 plus 3 into minus 3. 4. Again, first row, third column. 1 into 2 plus 2 into 1 plus 3 into 2. Again, first row, fourth column. Horizontally and vertically. You go like the corresponding I'm taking 1 into 3 plus 2 into 3 plus 3 into 1. I think that's clear. I took the first row and I multiplied corresponding with the elements of first column. One row, that's why I took here. This sort is coming. But because if here 3 won't come, automatically these two doesn't match. Because here I am talking about the rows and the corresponding rows with respect to columns, right? So here I am taking about the number of columns, 3, and here number of rows. I am taking those parts. Now how many elements came here? Automatically 4 columns came and 2 rows only will come. Now second row which starts with 4, 5, 6. 4 into 1 plus 5 into 2 plus 6 into 4. Again 4 into minus 1 plus 5 into minus 5 plus 6 into minus 3. Again third one. 4 into 2 plus 5 into 1 plus 6 into 2. Again fourth one. 4 into 3 plus 5 into 3 plus 6 into 1. Oh. Now 2 rows are multiplied with respect to each column. So automatically, oh, now you simplify it. Now what is the order of this element? You will see 1, 4 plus 1, 12 plus 4, 16 plus 1, 17. Here minus 1, minus 10, minus 11, minus 9, minus 20. So you should be careful doing 2 plus 2, 4, 4 plus 6, 10, 3 plus 6, 9 plus 3, 12. So here 10 plus 4, 14, 14 plus 24, 38. Minus 4, minus 25, minus 29, minus 29 plus minus 18, minus 47. 8 plus 5, 13 plus 8, 12. 13 plus 12 is 25. 12 plus 15, 27 plus 6, 33. This is 2 rows and 4 columns. This is the order. So this is nothing but I take as C. If AB is equal to C, this is the output of the matrix. You can make a note of this. Because this is very important to be able to do. Very clear? I'll show the reverse process also, how to go about it. But reverse is 3 by 4 into 2 by 3, not possible. BA is not possible. We'll discuss that. So matrix multiplication is not commutative since AB is not equal to BA. Most of the cases AB is equal to BA doesn't happen because matrix multiplication never completed and it is not feasible to be multiplied. If AB is able to get, BA need not be able to be possible. Right? Please make a note. So corresponding rows for row wise elements of the first matrix can be multiplied with the corresponding column elements of second matrix. So corresponding row elements of the first matrix should be multiplied with the corresponding column element. So here I can take here A11, A12, A13. Here I can take here B11, B21, B23. Sorry, B31. I can make it general also. Here Okay, now we'll see corresponding multiplication in general. You have noted, I think. If you have noted it, I can proceed to the next part. Please make a note of this because this is important to be able to understand carefully. Matrices, diagonal gates, principal diagonal gates, symmetric space. Okay. Right? Now, so I will generalize it. Right? So I want to find BA. So B is of the order 3 by 4 and A is of the order 2 by 3. Since 4 and 2 are not equal, BA is not possible. Actually, you have got it. Because you have to go with row wise to column. So if here 3 are there, here 2 only there, how will you multiply corresponding elements? See, if 3 are there, here 3 are there, automatically here rows are equal to here columns, then automatically you are able to do. But respectively, you are taking the row wise to column, right? So you are able to do, but when you are multiplying, you are taking columns, number of columns here. See, number of columns to here, number of rows. So here number of columns are 3, number of rows are 3 here. So here then you are able to find. Here number of articles say columns are here 4 and here number of rows are 2. How you multiply 4 elements with corresponding 2 elements? So there is no order possible to have the feasibility of the multiplication. That's why need not be if A is possible, then need not be A is possible. Then BA need not be possible. It can be possible sometimes. How? Right? So always clearly AB not possible, then automatically if possible also they are not equal. AB is not equal to BA. So matrix multiplication is not commutative. You know what is commutative? If AB is equal to BA, that is called a commutative operation. So matrix multiplication is not commutative. AB is not equal to BA. Never it has to be. Right? So if AB is possible, then BA also can be possible or not possible. Right? Whenever AB and BA both are possible, see here. Suppose if A is equal to 2 by 3 and B is equal to 3 by 2. So AB is possible and their order is automatically C is 2 by 2. Remove this part and you will get here 2 by 2. Suppose BA. BA is how much? BA is 3 by 2 and A is 2 by 3, right? Right, again this two are equal automatically. BA is equal to something D, you can get 3 by 3. So if the orders are reversed, if the order of the A is reversed with the order of B, then AB is possible and B is also possible. So if automatically A M by N is B is N by M, automatically the number of elements are the rows of the first column or number of columns of first row, first element matrix are reversed with the number of rows and columns of the second matrix, then AB and BA both are possible. Otherwise, not possible. So the basic condition for AB and BA, the part of two matrices to be feasible is that AB is possible and BA is also possible only when the orders of the two matrices A and B are reversed. It's M by N into N by M. But are they equal or not? We will see that also case. They will be never equal. That also we can discuss. So matrices multiplication is not always possible, and if possible also, they will not be equal. They are not commutative. That also we can verify now. Suppose I took here A 2 by 3 and B I will take 3 by 2. Right? Then both possibles is there now? B is 3 by 2. So 3 rows and 2 columns. So I can take only these two. Right? Now we'll see here AB. See, what is the AB output? Automatically A and B, these two are equal. AB output is C 2 by 2. What is BA? BA is 3 by 2 into 2 by 3. So BA will be equal to D, but order is 3 by 3. The orders are also not equal. This element has 4 elements, this matrix has 2 by 2, and this matrix has 9 elements, 3 by 3. How they can be equal? Simple logic. We can think of their equality, their orders are at least equal, the number of elements are equal, then we may think that their respective locations of each element will be equal. But if the number of elements are only here 2 by 2 with 4 elements, and here 3 by 3, the left over in the order, it is 9. So simply C can never be equal to D. Therefore, AB is not equal to BA. But to have AB and BA existable or feasible, you should have their orders are invertible. A is 2 by 3 and B is 3 by 2. Or A is M by P, then P by M. M by N, N by M. Otherwise, M by P, P by N, then automatically you will never have BA if AB is valid, or you will never have AB if BA is valid. If to have AB and BA are valid or possible or feasible, then you need to have their orders are revertible. Though they are available or feasible to have AB and BA, they need not or they should not be equal, since AB is found with 2 by 2 order and BA is found with 3 by 3 order, so they never be equal. So matrix multiplication is never commutative. That is what you take into standard way, right? Addition is commutative. A plus B is equal to B plus A. Subtraction is also not commutative because A minus B is not equal to B minus A. Associative property we discussed later, right? And multiplication is associative. A into BC is equal to AB into C. That part we discuss later. Now we are left with one more concept, that is symmetric and skew symmetric matrices. Right. Before going to that part, transpose of a matrix we'll see here. Transpose. If A is equal to, suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, then A dash or A transpose, both are same, O dash or transpose is equal to, reverse the elements of the rows and columns. Here, row is it should be column here. Now 1, 2, 3. Second row becomes second column, and third row becomes third column. So if rows and columns are interchanged, then it's called the transpose of the matrix. So if rows and columns are interchanged, the resultant matrix will be the transpose of the given matrix. So again it's a matrix, but order is same because 3 by 2 only here and there. Suppose I took here 2 by 2 or 2 by 3, 2 rows and 3 columns here. Automatically what becomes here, this becomes 1, 2, 3 and 4, 5, 6. Because row becomes column and this becomes here, what becomes here? Number of rows will be 3 and number of columns will be 2. So order also interchanges. Right? 2 by 3 becomes 3 by 2, A transpose. You can call A transpose or A dash, it's the same only, nothing but B also can use, you can take it. Right? Now always transpose matrices are each other multiplicand to each other. They can be multiplied because 2 by 3, 3 by 2. So A into A transpose you can go, or you can take A transpose into A also you can go. Right? Now what you multiply A into A transpose? 2 by 3 into 3 by 2. The order is that is C something. Right? So A transpose into A you can take as 3 by 2 into 2 by 3. So the order is 3 by 3, that you can take D. Again, they are not equal, but multiplication is feasible among A and A transpose because both cases the orders are being reversed. Because transpose concept is that only. They are invertible in the case of row odd number of rows and number of columns. Right. Now we'll see symmetric matrix. If A transpose is equal to A, then A is said to be symmetric matrix. And I can take here skew symmetric. another one property. If A transpose is equal to minus A, then A is said to be skew symmetric. We'll have a question on this part. This should be important. Verify that they are symmetric or skew symmetric. You have to verify them. So how we can go with the symmetric is A transpose is equal to A and A transpose is equal to minus A, then it's called a skew symmetric. I'll tell you an example to that. Yes, sir. 1 minute. Two and five. See here, I am taking an example here. A is equal to 215, 127, 573. So A transpose I can take it as rows becomes columns. So 215, 127, and 573. Now see here, both are same only. I interchange rows to columns. First row become first column, second row become second column, third row become, but both are equal. Right? So here A is equal to A transpose, then this is called a symmetric matrix. Right? Now what about skew symmetric? A transpose is equal to minus A, that's second case. So we'll see an example here. Okay. I take an example. A is equal to 012 minus 105 minus 2 minus 4 0. Now A transpose is equal to, you take it as 012 minus 105 minus 2 minus 5 0. Now see here 012, 0 minus 1 minus 2. Each element 0 and minus 0 has no change. 1 becomes minus 1 minus 2. Here 2 becomes. Here minus 1 becomes 1, 0 becomes 0, 5 becomes minus 5. Minus becomes 2, minus 5 becomes 5, and 0 is 0. So for each Aij belongs to A, Bij is equal to minus of Aij belongs to B. Then A is skew symmetric. So automatically you have to clear A transpose as B. So okay, for each element corresponding location has change in sign. Each element has. You can see the example like that. So that is called symmetric. So symmetric is directly if orders are changed, interchanged, that they are transposition, the elements are same. In the transposition taking place, the elements are negatives or changes the sign respectively, then it's called the skew symmetric. So we have a question on this symmetric and skew symmetric and their properties. And again, we have questions on multiplication of matrices and then addition, subtraction, their properties also we discussed. And after this, we'll go finally with the inverse of a matrix with the elementary operations. That is the closing session. So tomorrow we'll continue with some more elements. Today for this part, I will send the material to you. I think very simple. I think you are able to follow it. So we'll continue tomorrow with the same session. Right? Thank you.